Question 7. Find out whether A is orthogonally diagonalizable or not. To check this, it is actually quite straightforward because you just need to see whether A is symmetric or not. So for part A, yes, this is orthogonally diagonalizable because this is symmetric. This is also symmetric, hence it is orthogonally diagonalizable. For this is not symmetric, so it is not orthogonally diagonalizable. If it is, find a matrix P that orthogonally diagonalizes A and determine P transpose AP. For this, the steps are similar to the matrix P that diagonalizes A, but the main difference is just you need one more step, which is to normalize your eigenvectors. So I will just do part B because part A is just the same. C is not orthogonally diagonalizable, so I will not do C. So part B. So we consider 0 equals to lambda I minus A, and this is equal to determinant of lambda minus 1, 0, 0, 0 lambda minus half, half, and 0 half lambda minus half. And we use cofactor expansion on this row. So we will have lambda minus 1 multiply with lambda minus half take square minus half square. And this is just A plus B, A minus B, because this is A square minus B square. So I will have lambda minus half, lambda minus half plus half. So this is lambda minus 1, this is lambda. So I have lambda times lambda minus 1 square. So I have lambda equal to 0 or lambda is equal to 1. So we have two eigenvalues. So for the lambda equals to 0, we want to find x such that lambda I is minus A is equal to 0, but lambda is equal to 0, so it just means that I want to find x such that AX is equal to 0. In other words, 1, 0, 0, 0, half minus half, 0 minus half, half times x1, x2, x3 is equal to 0, 0, 0. Okay. The first row gives me x1 is equal to 0. The second row gives me half of x2 plus minus half of x3 is equal to 0. The third row gives me minus half of x2 plus half of x3 is equal to 0. And okay, this directly gives me x1 is equal to 0. These two equations, they are the same, right? Because I can just multiply by minus 2 here and 2 here, and they will be the same. So, okay, one of them is useless, so I will just look at this. This means x2 is equal to x3. So if I let my x3 to be a free variable, x2 will be just that free variable. So this means I have x1 is equal to 0, x2 equals to t, x3 equals to t. T is real number. Hence, x is equal to t times 0, 1, 1, where t is real number. And we can take this as our eigenvector. Let's call it v1. Okay. Let the v1 equals to 0, 1, 1 be an eigenvector of lambda to 0. Okay. And the set, okay, the set 0, 1, 1 is orthogonal, okay, but it is still not orthonormal, so I just need to change the length of this, okay, into 1 by dividing by the length of this. So the orthonormal basis, okay, for this eigenspace is okay, maybe I do need to write this. Yes, okay. Then an orthogonal basis for the eigenspace corresponds to lambda equals to 0 is 1 over square root 2 of 0, 1, 1. Okay, we are done with lambda equals to 0. Let's move on to for lambda equals to 1. So for lambda equals to 1, we want to find x such that I minus a x is equal to 0. In other words, what is my I minus a? So this will be 0, 0, and half, okay? 0, 0, 0, 0, 0, half, 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 times x1, x2, x3 is equal to 0, 0, 0. In other words, we have the first row gives me 0 equal to 0, so there is no information. Second row and third row, they are the same. Okay, so this has no restriction on x1, so I can let my x1 to be a free parameter. For x2 and x3, I make one of them to be free parameter. Let's say s is x3, so my x2 is minus s, where t and s are real number. Hence, x is just equal to t times 1, 0, 0 plus s times 0 minus 1, 1. Ts are real number. Okay, and now we pick this as eigenvectors for lambda equals to 1. And luckily, these are orthogonal, right? The set is orthogonal. We are very lucky here. If it is not orthogonal and you want to find the orthonormal basis, okay, sorry, this should be orthonormal. What you need to do is you apply the Gram-Schmidt process on these two vectors. So then an orthonormal basis for the eigenspace corresponds to lambda equals to 1 is 1, 0, 0. Okay, I just need to make the length to be equal to 1. 1 over square root 2, 0 minus 1, 1. Okay. And this of course they are linearly independent. Okay, so we have P is equal to, just this copy, 0, 1 over square root 2, 1 over square root 2, 1, 0, 0, 0 minus 1 over square root 2, 1 over square root 2. And P transpose yes, we are asked to find that. A transpose AP will be a diagonal matrix which entries are the eigenvalues. So for this case it is 0, 1, 1. Okay, and we are done. So for the part B, also try to give a geometric description on the linear transformation. Okay, I will make this, I will do the explanation on the next video.